Hey, hi class. Let's solve the last problem for the thermodynamic analysis exam. So this is the problem. We already read this during the class. A refrigeration cycle is to be used in the production of a continuous supply of chilled water at a temperature of 10 degrees and at a rate of 25 degrees. So the goal is to supply chilled water at this temperature, and this is the rate of the chilled water. So take note, this is not the mass flow rate of the refrigerant. This is for the chilled water. Now, the refrigerant circulating in the cycle is water. So you may use the steam table since it's water. Saturated steam at 0.008 bar enters an adiabatic compressor. Take note, adiabatic with this efficiency 80% based on isentropic operation. So in the compressor, it's compressed to 0.07 bar. So at the exit of the compressor, this is the pressure. It emerges as a saturated liquid from the condenser. The saturated liquid flashes through a valve. So it acts as a throttle valve. So if you will remember, for throttle valves, it's isenthalpic, which acts as a throttle to reduce the pressure to 0.008 bar. The remaining liquid is vaporized in the evaporator, producing saturated vapor. The water to be chilled also passes through the evaporator, and by heat exchange with the evaporating refrigerant is cooled from its feed temperature of 27 to 10 degrees. So the original temperature of the water that is to be cooled is 27. So take note, this is not the refrigerant. This is the supply of chilled water. The required is make a thermodynamic analysis of the process if the surrounding temperature or T0 is 27 degrees. Am I recording? Okay. So this is the schematic diagram and this is the TS diagram. Let's analyze the process once again. Our refrigerant is water. Okay, the first step is from the problem enters an adiabatic compressor. So this is the pressure as it enters the adiabatic compressor. And since it's a work requiring device, there is a work shaft input. As it exits the compressor, it leaves at this pressure, 0.07 bar. And then it enters the condenser, and after it exits the condenser, it exits as saturated liquid. So in the TS diagram, this is the compressor. There's work in or work input. It enters as a saturated vapor. In the problem, it was not given, but we can assume that it enters as a saturated vapor, okay, based from the TS diagram. And at the exit, it exits as superheated steam. And then this part here is the condenser. It enters the condenser, and as it exits, it becomes saturated liquid. Okay? And then it enters a throttle valve. Supposedly this should not be a straight line, it should be a curved line to represent the throttle valve. Okay? And then wherein after it exits the throttle valve, it becomes a wet steam. A wet steam at this pressure. So this is the evaporator. If you will remember, it is where QC is absorbed. In the condenser, it's where QH is released. So in the evaporator, okay, the chilled water actually exchanges heat. Okay, so the evaporator takes in the heat from the chilled water, and the chilled water reduces temperature from 27 to 10 degrees. And the mass flow rate of the chilled water is 25 kilograms per second. This is not the mass flow rate of the refrigerator. Okay? The first step, just like our previous examples, would be to make a table. Insert table. Okay, let's build a table. This is the step. The state, the pressure in bars, H in kilojoules per kilogram, S in kilojoules per kilogram Kelvin. Step 1, oops, 2, 3, 4, 5, 6. Okay. In step 1, we know that it's wet steam. Wet steam. Do we know the pressure? Yes, we know the pressure. It's equal to step 2, okay, which is 0.008 bars. 0.008 bars. So can we read this from the steam table? Yes, we can read it from the steam table, but let's do that later. Right. Let's go to step 2. Saturated vapor. Okay, saturated vapor here at this point. So, saturated vapor at the same pressure because it happens in the saturated region. So, it has to be the same temperature and same pressure. The next stage is step 3, superheated steam. Okay, superheated steam. And the pressure is 0.07 bar. Step 4, saturated liquid. And do we know the pressure? Should be the same as this one because this happens at a constant pressure. This is an isobar, so it should be 0.07 bars. Next is 5 and 6. So 5 and 6, let's assume that we don't have subcooled property tables. So we can assume that this chilled water is in saturated liquid form. Okay, this chilled water, supposedly it should be subcooled water, but since we don't have the property tables, we can assume that it's saturated, purely saturated liquid. Okay? We don't know the pressure, but we know the temperature. So let's just put here the temperatures. 10 degrees Celsius. Okay? So as it exits, it's 10. Okay. Let's start with point 2 or step 2. Let's make a new. So step 2. Step 2. P2 is, let's now convert this into kilopascal. So the conversion is 1 times 10 to the 5 bars is equal to 1 bar is 1 times 10 to the 5 pascals. So 1 bar is 1 times 10 to the 2 kilopascals. So multiply by 100. So that is 0.8 kilopascals. So at point 2, okay, we can read it from the steam table in the saturated vapor column. Saturated vapor column at this pressure. Unfortunately, there's no direct data, so we need to interpolate by interpolation. Okay. So we can read it by interpolation. HV, or the vapor, saturated vapor, is H2 equal to 2508.48. SV equal to S2, okay, 9.05861. Let's update our table. So that is from steam table via interpolation. Okay. Next, let's try step 4, saturated liquid at 0.07. Step 4, pressure 4 is 0.07 bar, so times 100, 7 kilopascals. Similarly, we can get this by interpolation. Okay. So this time, HL equal to H4 equal to 160.4. So the unit is kilojoules per kilogram for enthalpy, and for entropy, the unit is kilojoules per kilogram Kelvin. SL 0.5591. Let's update our table. So again, this is from steam table by interpolation. Okay. Let's now try point 1 or stage 1. Since this is a throttle valve, that means that H1 is equal to H4. So we can copy that. H1 is just equal to H4 since throttle valve. Step 1. What's the pressure? Step 1.008, so P1 equal 0.8 kilopascal. Since it's a throttle valve, H1 equal to H4 equal to 160.4. Okay? Next is to solve for the quality. Okay? Since we are in the middle of the saturated region, it's not our point 1 is not on the saturated liquid curve, it's not on the saturated vapor, so there must be a quality here, X. So we can solve it if we know the properties of the vapor and liquid, which again is from the steam table at 0.8 kilopascal. So by interpolation, HL is 15.825, HV is 2508.48. So to solve for x, for the quality, so let me write that equal to HL 1 minus x plus HV times x, correct? So this is 163.4 equal to HL 15.25 times 1 minus x plus HV 2508.48 times x. Solving for x, solving for x, 0.0592. Okay, 0.0592. Now let's solve for S4. So from the steam table, SL is 0.05757, SV is 9.05861, 9.05861. Entropy of vapor is larger compared to entropy of liquid, 9.05861. Okay. Then solve for S4. This is equal to x times 1 minus x na lang. 9.0586 times x. Sige. Tapos 0.0592 times 1 minus x. Okay. So this is S4. You will get 0.5904. So let's update our table here. Okay? Okay. Now let's move on to step 3. Step 3, this is a superheated steam. Okay, superheated at this point. Step 3, after exiting the compressor. So what you need to do is first assume isentropic compression. If that's the case, then S3 equal to S2 equal to S3 prime. Okay, S3 prime equal to 9.05861. Correct? So the pressure here is in kilopascals. Okay, kilopascals. And then check the superheated properties of the steam table. So since so this is this is one phase only, superheated steam. So we need two properties. We have the pressure and we have the assumed isentropic entropy. So we have two properties. From the steam table, you will see something like this. Okay, because you need to interpolate again. Okay. Temperature, degrees Celsius, entropy, and so 25 degrees Celsius, 175 degrees Celsius. So at this pressure, 7 kilopascals, which is via interpolation. Okay. So this is via interpolation. 927 2735.5, and this is 9.359. 2831.4. Okay. I think this is double interpolation. So, I don't have my steam table right now. Just, I leave it to you to check it. So, this is the first interpolation. Then, you have to interpolate in the middle. 5861. Okay. To get H3 prime. Okay. 2791.1. So this is via interpolation. H3 prime is, oh no, 2791.1. Okay. The next step is to make use of the efficiency equal to work shaft over work shaft, but which is the isentropic work? This is smaller for a work requiring device. So this is H3 prime minus H1 over H3, I'm sorry, it should be H2. H3 prime minus H2 over H3 minus H2, and this is equal to 0.8 the efficiency. So H3, rearranging the equation, solving for H3, I leave it to you. It's just plugging values to the equation, 2861.76. Okay. So this is the actual H3. Okay, the H3 actual. So let's update our table. Now we solve for S3. We solve for S3. So since we have the actual H3 and we have the pressure, we can use it to interpolate S3. So how do we do that? Again, it's via double interpolation. So I leave it to you to solve it. You have to do a double interpolation. Anyway, I'll just show you. By interpolation, so we have pressure. We have so this is pressure. This is temperature. Temperature 175 degrees Celsius, and this temperature here is 200 degrees Celsius. Okay. So 110. So these are the given values in the steam table. 8.7994, 8.9045. So you have to interpolate twice again. Okay. Insert column to the left. So the first interpolation is this one. Okay. This one at 7.39. first interpolation at this temperature and pressure. The next part is the second interpolation. So that is your value. This. Okay. So 1 minute break. Okay. And the next step is, what's the next step? So we have all these values here. How about for 5 and 6? We can directly read it from the steam saturated liquid properties since we already have the temperature. So it's just merely reading from the steam table. So still recording. 3949 1510. Okay. So the next step is to make our thermodynamic analysis table. So let's solve for work ideal. But before that, for a work requiring process, so it's our table. Our table should look like this one. Okay. Let's solve for work ideal. The formula is delta, insert symbol, insert delta H minus T naught delta S. This is equal to get the work ideal, we need to, so remember in our previous problems, we get the work ideal by evaluating from the very start of the process to the very end. So for example, we have this process right here and we have sub-steps. Say we have a condenser and then cooler. The work ideal is evaluated from this point to this point. So it encompasses every step. But this problem is a cycle. So where do we get the work ideal for a cycle? So if this is a cycle, it's a loop, it's closed. There's no way we can get the end and the start unless we consider these points 5 and 6 as our end and start, which makes sense because the work being done here is actually the absorption of QC in the evaporator. It's not work per se, it's heat. Okay, it's in the form of heat. There's no moving parts. Okay, but again, this part here represents the whole cycle. So this is the start and this is the end. So for cycles, you have to get the work ideal from, you still have to get it from the start and the end of the process. But since it's a closed cycle, then you have to find a representative stream of the start and end of the process. Okay? Let's just use the formula delta H minus T naught delta S, which we derived from class. So that is H6 minus H5 minus T naught S6 minus S5. Okay, substitute the values which we got from the steam table. Just substitute, you will get 2.0966 kilojoules per kilogram. Okay, then let's convert this to power. So multiplied by 25 kilograms per second. Okay, so why do we need to multiply by why do we need to convert into power? Remember, we have two streams. Okay, we have two streams. We have the chilled water and we have the refrigerant. So we cannot have a basis of per kilogram because the mass flow rate of the chilled water is different from the mass flow rate of the refrigerant. But we can have a basis of per second, or in terms of kilojoules per second, or power, since second or the time is the same for both streams. Okay, so since we have two streams, we need to have the same basis for both, and it cannot be mass. So 2.4146 second. Okay. Okay. The next step is to get the work shaft. Okay. Get the work shaft. So the work shaft should be taken here. Should be taken here. Okay, again, so why do we use points 5 and 6 for the work ideal? Okay, because it's where the work is it is where the work is needed for the chilling of water. Okay. So for the work shaft, H2 minus H3 minus H2. This is the compressor. So just substitute H3 and H2. You will get 353.28 kilojoules per kilogram. But we need to multiply this by the mass of refrigerant, okay, which is not given to us. So how do we get the mass of the refrigerant? We make an energy balance around the evaporator. So around the evaporator, if we assume it's perfectly insulated, then delta H is just equal to 0 if it's perfectly insulated. Okay, so if that's the case, all the inputs and all of the outputs Okay. We just equal to 0. So we add all the inputs. Output minus input is just equal to 0. Or, so what are the outputs? H2 and H6. H2 and H6. But we need to multiply by the corresponding chilled water, corresponding mass flow rates. Okay, so MCW for mass flow rate of chilled water. So those are the outputs minus the inputs. Inputs H1 and H5, and we need to multiply by the mass flow rates equal to 0. Okay? So, rearranging so that all the mass flow rates are, all enthalpies with the same mass flow rates are grouped together. So everything here is known except for mass flow rate of refrigerant. This is known, this is known, this is known, everything is known. MREF, solving for MREF, you'll get 0.758. So this is the mass flow rate of the refrigerant. Continuing our solution right here. So in terms of power, this is 267.82 kilojoules per second. Okay. Work lost in the compressor. T naught delta S. T naught delta S minus Q. Okay. So, this is equal to the temperature in absolute value, S3 minus S2. Compressor is adiabatic, so this is 0. Plugging in S3 and S2, I leave that to you. Okay, and then multiplying this quantity by the mass flow rate of the refrigerant, you will get okay, let me calculate that. S3 0.7 37.15 okay, kilojoules per second. Then condenser, okay, if we make an energy balance around the condenser, Q is just delta H. So you will get Q equal to delta H, so that this is just equal to um, so everything is known here, just plug in into the equation. Okay, sorry, my mic was off. Work loss in the throttle valve using the same formula. Okay. T naught, so in the throttle valve, it's between points 1 and 4. T naught S1 minus S4. For throttling process, delta H is 0. So if we make an energy balance around the throttle valve, okay, you will get delta H equal to 0. So this is 0. Plugging in everything and multiplying by by the mass flow rate of the refrigerant. This is kilojoules per second. Lastly, work lost in the evaporator. So in the evaporator, there are two streams. Okay, there are two streams, stream 1 to 2 and 5 to 6. So our T naught there should also be 2. 2 minus S1 times mass of the refrigerant. So this is for the refrigerant stream, and then another one for the chilled water stream. Minus Q. So we assume that it's perfectly insulated, so that is 0. Now, plugging in the values, you'll get 96.72 kilojoules per second. Okay, so let's make the table now. So this is in kilojoules. This is in percent. Work ideal. 52.4 summation of work lost. So we have compressor, condenser, throttle, valve, evaporator, work shaft. 38.34 compressor. Oops, mali. 37.16. Okay, let's add this. The total is 215. Let's add everything. Okay, the total is 267.87. Our work shaft calculated is, where's the work shaft? This one. So 267.82, which is close. 267. So the total of the work ideal plus the work lost is this value, 267.87. And our calculated work shaft is 267.82. So that's good enough. That's close enough. Oops. Okay, let's now put the percentages. 36, 2.66, 36.10. This should be 100. So we can see here that the biggest work loss is in the condenser. And the total of all the work lost is this one, 215. We only need this work ideal, this amount of work ideal, 52, and the work loss is as big as 215. Okay, so that ends the problem. If you have questions, just message me since there is no class today.